Hi everybody. What I wanted to do here was give you a brief rundown of hexadecimal and decimal um, and binary and the area of Arduino programming. And I call this little lecture The Role of Radix, where Radix refers to the base of the numbering system that you're using for the programming. What we find is that binary numbers and hexadecimal numbers are typically used in microcontroller programming. Sometimes we see octal being used, but it's quite rare nowadays. It used to be common for the PDP-8. Of course, bit is an abbreviation for binary digit, and there are 8 bits to a byte. And 4 bits are called a nibble. And typically, if you've had your Digital Design 1 class in recent memory, you remember how to convert from binary to hexadecimal. You divide things into 2 nibbles, the lower and upper nibble, and then you assign letters or numbers to the 4-bit grouping. You can count from 0 to 15 using these numbers, and the way you organize them is you want your least significant bit to be on the right and your most significant bit to be on the left. Some people call this Little Indian, E-N-D-I-A-N. Others call it Big Indian when you reverse it. That would be for the IBM computers. So typically, using positional notation, we can take a binary number and convert it into take a decimal number and show how it can be converted into a value using the radix, the base, and then the exponent based on the position, hence the name, positional notation. And so this is common for you guys. You've seen this before. Decimal is what you grew up with. In binary, we can do a very similar thing with positional notation to get a value. And here we can see 2 to the 3 is 8, 2 to the 2 is 4, and then 2 to the 0 is 1, and we add these together to make 13. So the binary to decimal conversion is a relatively straightforward thing. No divisions are required. And we are able to count from 0 to 15, but we use letters A through F for numbering 10 through 15. So that's the total number of values. That's 16 values, including 0. And why do we care about hex? Well, it's a convenient way to represent the binary. And we're going to use that binary in order to do our programming. So typically what we do is we can set up a little, this is almost like a truth table, binary numbers and then the corresponding hexadecimal equivalents. And each one of these bits correspond to a specific function in a register. This is the so-called oscillator calibration register. This is used to trim the calibrated internal resistor capacitor oscillator and remove process variations. And you can actually write numbers into this and change that oscillator, although I must admit I've never done it. In point of fact, you can take some sort of binary number and encode it directly as a literal by preceding it with 0 and lowercase b. The term will be used as a binary number, but if you prefer, you can use hexadecimal. It's 0x is the preceding letter, and then 5a will be regarded as a hexadecimal number. And so that's the way in which these things can be encoded. You may prefer the binary, and that's fine. It'll work the same. The compiler doesn't care, and it won't be any faster or slower. So now you can see how the mapping from nibbles to letters occurs. C corresponds to 12, 111 corresponds to 7, and here we have 99 being shown in 2 nibble form. And then if you wanted to convert 99 in hexadecimal to a decimal number, it would be 9 times 16 to the 0 plus 9 times 16 to the 1. So then you would get 153. So this is a common way in which to represent this stuff. And so how do I change the data direction register without doing it one bit at a time? I want to set all the bits at once. So this is data direction registers associated with ports. So here's data direction register for port B. And now what I can do is I can write out the ones and zeros all at once to this port. DDRB is data direction register B. And in the process of doing this, if I put a 0 out there, it's an input. If I put a 1 out there, it's an output. And so that gives me an opportunity to change every single bit all at once, and this is quite a bit more efficient. Get it? A bit more efficient than trying to do it one bit at a time. And it's especially useful if you're taking all 8 bits and turning them into inputs, and then taking all 8 bits and turning it into outputs. So that's quite typical. You might need 8 bits to go out and then 8 bits to come in. So that's for reading and writing from a given port. And so here we have some port details. And now we have the actual port data, called port D. And now here's the data direction register for port D. And so now you can write all the bits all at once to the data direction register and then output data to port D. And so that's kind of nice. And the way things are set up here is we have tri-state logic and latches going in both directions. So we can have a latched register write, and a data direction register is really nothing more than a bunch of D flip-flops. And those D flip-flops can essentially serve as 1 bit of RAM each. And so you'll probably get something like an octal bus transceiver for your implementation if you try to do this in TTL. But that'll all be integrated into the microcontroller. So if you wanted to make pins 3, 5, and 7 all outputs, you can just write bits to this 1 bit at a time. Or if you're going to use a header file that defines which pin is which for the D register, you could include that header file and then use these symbols. But here's the alternative approach, right? Now we see 0, 1, 2, here's bit 3, 4, 5, there's bit 5, 6, and 7. So now these are being used as your outputs and all the rest are being used as inputs, and you can just do DDRD equals, and that's going to set the data direction register the way you want it. And if you wanted to, you could use it as a hexadecimal quantity, and you could see 1010 is corresponding to 8, whereas 1000 is corresponding 1000 is corresponding to 8, and 1010 is corresponding to A. And here's another way to go. You could do the shifting to the left by the actual number of the pin, and then that'll essentially get you to where you want to go. This will be pin 7, it'll be pin 5, and then here comes pin 3. And so that's using an inclusive OR after the shift is done, and then setting the data direction register. So that's a cool way to go. And now we can do a digital write to pin 0 on high. That'll output a 1. And if you wanted to, you could use this header file and use the actual symbols. And here we have input pins 0 and 1 being set so that we can write to them, so they become output pins, and we can use the hexadecimal quantity 3. Now, here's another way to go. You can use an AND operation, and then you can start using interesting bit flipping. That in and of itself, it looks a little bit more like clever code, and I can't encourage it. So here's an overview of a sketch. I'm going to unpack and describe the pieces in a little bit more detail later, but we can see now how the pin mode is being set to output, and setup is the first thing you do when you run the program. And essentially it takes an init, right, and calls it just once, and that's a critical thing to getting your code configured. They call this a sketch. Why, I don't know. Looks like a computer program to me, but there it is. The loop that runs forever, and so you got to be kind of careful about how much computation you do in this thing, or else none of your interrupts will get serviced properly. So throwing in a little bit of delay now and then will actually help interrupt service routines run a little bit more regularly. And we may recall the idea of having pull-up resistors in order to be able to get a voltage for when you close this switch. When you close the switch, this voltage here on PD3 is going to look as though it's 5 volts. When you open the switch, it'll look like 5 volts. When you close the switch, it'll look like ground. So that's a main technique for handling the inputs. And now we have, I think, seen a good application for hexadecimal and binary in our Arduino programming. And that kind of gives you a basic idea of the role of Radix in Arduino programming. Here we have a defined, this is a macro. The pin switch will be 3. And then latched is of value low, which would be like a 0. And then we take this pin switch 3 and the input pull-up, and this allows you to essentially get a pull-up resistor associated with the input switch. And let's see if there's anything else here we need to do. So here's an opportunity where you have a switch. If it closes, how do we know what the value will be? And right now it's kind of undefined. And that's a problem. And here's a light, and we'd like that light to light up when the switch is closed. That's on PD2. And there's a buzzer, which is on PD3, which will go off maybe if people aren't wearing their seatbelt. So we add the pull-up resistor, and then the pull-up resistor essentially allows us to have a defined value here on PD0's input. So that's a basic idea for our programming with hexadecimal and binary. Hope you like my little presentation. And that's what I have for you for today. Thanks a bunch. Talk to you later. Bye.